Welcome to Module 4, Physical Layer. After 2 modules on protocols and models, this is where we get concrete again. Actual cables, connectors, and signals. Frame it as, everything we discussed as abstract layers now becomes physical hardware you can hold in your hand. Objective: explain how physical layer protocols, services, and media support network communication. Preview the topic table on screen. Purpose of the physical layer, its characteristics, copper cabling, UTP specifically, fiber optic cabling, and wireless media. This module sets up cabling knowledge they'll use in every lab going forward. Before any communication happens, a physical connection has to exist, wired via cable or wireless via radio waves. Give the everyday example. Office desktops cabled to a shared switch versus laptops and phones connecting to a wireless AP. Both are physical layer, just different media. The physical layer's whole job: take a complete frame from the data link layer, encode it into electrical, optical, or radio signals, and send those signals 1 bit at a time across the media. The receiving device's physical layer reverses this, decoding signals back into bits, then handing a complete frame back up to its own data link layer. Physical layer standards come from electrical and communications engineering bodies, not software groups like IEEE. Makes sense, since this layer is about actual circuitry, connectors, and cabling. 4 groups shown on screen: ISO, ITU, ANSI, TIA, EIA, cabling, IEEE, hardware and signaling, and national regulators like FCC and ETSI. Physical layer standards cover 3 functional areas: physical components, encoding, and signaling. And this slide covers the first. Physical components are the actual hardware, NICs, interfaces, connectors, cable materials, and designs. A router's ports and connectors are a direct result of these standards. Encoding converts a stream of data bits into a predictable pattern both sender and receiver recognize, similar to Morse code. Manchester encoding, voltage transitions representing zeros and ones, was used in old 10 megabits per second Ethernet. Faster speeds need more complex schemes like 4B/5B for 100 base TX and 8B10B for 1000 base T. Signaling is how the physical layer actually generates the electrical, optical, or wireless signal, representing a 1 or 0, shown on screen as a voltage over time waveform. Could be as simple as a long pulse versus a short pulse, similar to Morse code using long and short tones or flashes. Bandwidth is the capacity of a medium to carry data, measured in bits per second. Walk the unit table on screen. BPS up through kbps, mbps, gbps, tvps, each 1000x the last. Determined by both the physical media itself and the signaling technology used on it. 3 related but different terms: latency, total time including delays for data to arrive; throughput, actual measured bits transferred over time, usually lower than bandwidth; and goodput, usable data only, throughput minus overhead, always the lowest of the 3. Bandwidth is the theoretical max. Goodput is what you actually get. Copper is popular because it's cheap, easy to install, and has low electrical resistance, but it's limited by distance and interference. 2 specific problems: EMI/RFI, external interference from radio, fluorescent lights, motors, and crosstalk, signal bleeding between adjacent wires inside the same cable, shown in the diagram. 3 main copper cabling types, coming up next: unshielded twisted pair, UTP, shielded twisted pair, STP, and coaxial. Each fits different situations based on cost, distance, and interference tolerance. This slide is just the roadmap before diving into each. UTP is the most common networking media, terminated with RJ45 connectors, 4 color-coded twisted wire pairs and a flexible jacket, shown stripped back in the photo. The twisting itself is what protects against interference from neighboring wires, which is why untwisting UTP during termination hurts performance. STP adds shielding on top of twisting, better noise protection than UTP, but more expensive and harder to install. Structure shown in the diagram: 4 individually foil-wrapped pairs, then an overall braid or foil shield, then the jacket. Important gotcha. STP needs proper grounding, or the shield itself can act as an antenna and pick up unwanted signal. Coax gets its name from 2 conductors sharing the same axis: copper core, insulation, braided shield, outer jacket shown in cross-section. Largely replaced by UTP for Ethernet, but still common for antenna connections on wireless gear and for cable internet inside customer premises. Point out the 3 connector types on screen: BNC, N-type, F-type. UTP has no shielding at all. Instead, it counters crosstalk 2 ways: cancellation, opposing magnetic fields between paired wires cancel out interference, and varying twist rates. Each color pair twisted a different number of times per meter per TIA/EIA spec. The photo shows this. Notice the orange pair's looser twist compared to the blue pair. UTP follows TIA/EIA 568 standards, with IEEE rating cables into categories by bandwidth capacity. Walk the table. Cat 3 was originally voice-only. Cat 5/5e handles 100 to 1000 megabits per second. Cat 6/6a7 add pair separators for up to 10 gigabits per second. Cat 8 reaches 40 gigabits per second. Cat 5e is the current practical minimum. Cat 6 is recommended for any new install. Two wiring conventions contrasted on screen. Straight through, same standard, T568A or T568B on both ends. The common case connects unlike devices like host to switch versus crossover. T568A on one end, T568B on the other, connects like devices, switch to switch, or host to host. Node crossover is largely legacy now, since Auto 1509 auto-detects cable type. Fiber transmits data further and faster than any other media, with less attenuation than copper and complete immunity to EMI/RFI. Physically, it's an extremely thin, flexible strand of pure glass, barely thicker than a human hair, with bits encoded as pulses of light bouncing down the core, shown in the cutaway diagram. Two fiber types compared on screen. Single-mode fiber, SMF, has a very small core, uses expensive laser tech, sends one straight light path, and is used for long-haul telephony and cable TV over hundreds of km. Multi-mode fiber, MMF, has a larger core, uses cheaper LED tech, bounces multiple light paths, and is the common choice for enterprise LANs. 4 fiber use cases shown on screen. Enterprise backbone cabling, fiber to the home, FTTH, for always-on residential broadband, long-haul networks connecting cities and countries, and submarine cables surviving undersea conditions. Be clear with students. This course's focus is specifically the enterprise use case. Fiber connectors terminate the end of the fiber strand. Types differ mainly in dimensions and coupling method, shown in the photos. SC, square push-pull, LC, small square with latch, ST, round bayonet style, and duplex LC, 2 fibers in one housing. Mention SFP transceivers, as how switches/routers commonly accept fiber connections. Fiber patch cords use color coding to indicate mode at a glance. Yellow jacket means single mode, orange or aqua means multi-mode. 4 example patch cords, shown on screen with their connector combinations. This color convention is worth memorizing, since it's an instant visual check in a server room or wiring closet. Direct comparison table on screen. Fiber wins on bandwidth, up to 100 gigabits per second versus UTP's 10 gigabits per second, and distance, up to 100,000 meters versus UTP's 100 meters, and is fully immune to EMI/RFI and electrical hazards, but costs more in both media and installation skill required. Fiber is mainly used as backbone cabling and for connecting buildings on a campus. Wireless is the third physical layer option, and now the primary way most users connect. 4 limitations shown on screen. Coverage area, blocked by walls and terrain. Interference, from cordless phones, microwaves, fluorescent lights. Security, no physical media needed so transmissions can potentially be intercepted. And shared medium, half duplex, more users means less bandwidth each. 4 wireless standards, shown in the table. Wi-Fi, 802.11, contention-based WLAN using CCNA. Bluetooth, 802.15, short-range WPAN device pairing. WiMAX, 802.16, point-to-multipoint broadband. And Zigbee, 802.15.4, low-power IoT industrial use. Wi-Fi is what students will work with most in labs, but recognize the others by name. A WLAN needs 2 device types. A wireless access point, AP, which concentrates wireless signals and bridges to the wired network. Home routers combine router, switch, and AP into one box. And wireless NIC adapters, which give end hosts their wireless capability. The photo shows a typical home router providing both wired and wireless connectivity at once. Recap each bullet as the close. Physical connection required before any communication. Physical layer encodes frames into signals sent bit by bit. 3 standard areas. Components, encoding, signaling, bandwidth versus throughput versus goodput, the 3 copper types, fiber's bandwidth/distance/EMI advantages at higher cost, and wireless trading cabling for mobility with its own trade-offs.